Okay, well today we're dealing with electrical protection and prevention on a construction site. We're going to be dealing with electrical shock, arc, and blast. We're going to be dealing with power cord hazards, the hazards of working near overhead lines, and discussing how to minimize risks associated with working around electricity. So there's some trade terms in here, and they're very useful, and we'll deal with them, but I'm going to skip past them during this video. But they are in here for your reference, and they're useful and important terms. In this series for this exam, we are dealing with the top 4 things that are fatal on the construction site. Falls are the big one. Then struck-bys and electrocutions are pretty much neck and neck. Some years electrocutions are second, most years struck-bys are second. And then there's caught in or caught between hazards. So we've discussed these at other times, but here we're dealing with electrocution. So first of all, the OSHA standards for construction, 1926 400 through 449, that is the basic electrical standards. And you see how there's 2 standard groups that I've highlighted in boldface, dealing with 1926 404, wiring design and protection, and then 1926 405, wiring methods, components, and equipment for general use. Well, those sections also show up in the general industry standards, and they're very similar on this next page right here, where we see, again, 1910 304 and 1910 305. So this whole range runs from 1910 301 to 399, and then there's a subpart appendix dealing with electrical tables and charts and such. But the thing I'm pointing out here about these wiring design and protection and wiring methods and components sections is that there's not enough information in these sections. I've got them listed here up at the top in those 4 bullets. Again, there's not enough information, not enough detail within these standards for you to wire up a building of any kind. So OSHA defers to other standards, what they call incorporation by reference, like you see here in the boldface down lower in the page. They're using the General Duty Clause, Section 5A1, as the way that they issue citations when you haven't followed the National Electrical Code, for instance, the NFPA 70, or the ANSI standards dealing with equipment, the Underwriters Laboratories, or UL listed equipment and such. And it's not just them. The courts will also adopt these additional standards in their lawsuits and trials, and ultimately in settlements. And even in criminal proceedings, it can come up when there's willful violations. So the National Electrical Code, NEC, we sometimes abbreviate it as, is really and truly the NFPA 70. The National Fire Protection Association manages our national electrical codes, and so that formal name is the NFPA 70. And then there's a shorter booklet that deals with electrical safety in the workplace for all kinds of settings, from flipping burgers to the J.C. Penney clerk to working on a construction site. This standard, NFPA 70E, applies. So that's a simpler standard. It deals with electricity in the workplace. Then the ANSI standards, of course, we're dealing with many safety standards dealing with equipment. They oversee the development of voluntary consensus standards for products, services, processes, systems, and personnel. Then there's the Underwriters Laboratory, or UL listed equipment. And they're similar, but they deal specifically with certain kinds of equipment. And then any manufacturer's manual, you see item number 4 down here, every manufacturer's manual for equipment of any kind, really, but electrical equipment specifically here, can be cited by the Section 5A1 General Duty Clause by OSHA. And so they're all legal documents that are adopted by reference or incorporated by reference, 2 different ways of describing the same thing, by OSHA. Okay, so here's one standard that deals with this specifically within the National Electrical Code, and it's maybe the most important area for electrical. It's grounding. So grounding is not really tied down well within the OSHA standards, but it is very well specified within the National Electrical Code. You either ground with an 8-foot grounding rod that's 5/8 diameter copper, or you drive a 3/4 inch pipe into the ground and you connect to that, one or the other, and you need the complete 8 feet of that rod to be in the ground. And then you connect a wire to it like you see in this picture. Or you can literally bury the whole rod horizontally in the ground, 30 inches below, 2.5 feet. Or there's another weird exception where you can connect up to 20 feet of rebar that if it's embedded in the concrete that is directly in contact with the soil. Well, the typical slab for a building has a plastic sheeting membrane, a vapor barrier, underneath the concrete slab, and so that concrete slab is not in direct contact with the soil, so it does not qualify. Portable generators and pumps are often a culprit, especially when you're renting this equipment. They'll come sometimes with a 3-foot piece of rod, or something a little less than 3 feet, maybe 33 inches long, yeah, about that. So that because they'll take a rod that's 8 feet long and they'll cut it in thirds, and then they'll connect a cable to it, and then you should drive that into the ground. It is better than nothing. I'm not saying it's not doing some grounding, but it won't keep you from getting an OSHA citation. Okay, there's some things you don't need a standard for. You can figure this out. This is not right. This can't work. So some things you say would be common sense, but common sense isn't always as common as you might think. So in general, plumbing and electricity should not mix. Water and electricity shouldn't mix. And then I jumped over here to a toaster that I put up here, a real nice shiny toaster. You know, the wires inside your wall are not supposed to heat up. It's okay for a toaster wires to heat up because that's browning your toast. That's set up that way. But you do not want the wires in your wall to heat up, or the wires that you've plugged into the wall. The wires in the wall are purposely sized just right so that the breaker will trip instead of those wires heating up. But when you come to puny little extension cords that you hook up to that outlet, those things can start heating up and cause an electrical fire, and never quite until it's too late trip the breaker, because those puny wires are just not consuming as much electricity as they arc between each other as the insulation melts and breaks down and allows the 2 wires or 3 wires to arc against each other. So overloading cords and outlets can lead to fires. And that's what the arc fault circuit interrupters, AFCIs, protect against that. Not everybody seems to understand you don't stick strange things in outlets, and so people do. Like what you see at the bottom left corner, where somebody literally hooked up wires into slots instead of having a little plug on the end. And this poor guy's hairstyle has changed. So we got to protect people from themselves many times. So one of the ways we do that is by having dangerous high voltage equipment locked up in cabinets, in mechanical rooms and such, behind locked doors. And we put high voltage transformers we put up high in the air on top of power poles to keep them away from people. You know that when you go into a mechanical room, there's a lot of metal, and there's a reason for that. The metal will shield you from the electrical fields of these currents. When you have high voltage around you, you can have a lot of electrical current. Even in your house, the highest current area is right over there by the surface panel, the circuit breakers where they're at. And that's all enclosed in metal on purpose to protect you from those electrical fields so that there's no chance that you're going to receive an induced current, because they shield them. They thought that through. So when you take the cover off, that starts to defeat that safety protection. These cabinets that are in this mechanical room over here on the right hand, we put the wires in metal conduit in industrial facilities and such, and in commercial places many times too. And metal electrical boxes and conduits, that shields you from that electrical field. So we also keep the wires up high. And so the wires that come to your house are generally insulated wires, so there is a level of protection there. But some of those wires can be up there for years, and maybe the insulation is not as perfect as it used to be. And when you get when the electricity comes down into the house, into this panel without the cover on, like both of these pictures have an electrical panel without the cover, well, that is a dangerous condition. You know, people do take them off that know what they're doing, but you shouldn't be taking that cover off unless you know what you're doing. This is kind of showing the various ways of grounding in the left-hand picture. In the right-hand picture, in this case, the wires are coming from overhead, like the picture in the previous picture. There's 3 wires that come into your service panel from the meter, and they come from the power pole to the meter and then to this panel. And up at the very top, you see those 3 heavy wires. On each side, the black insulated wires are the hot wires that have 120 or so volts each. And the middle wire is the neutral wire. That's the return path to the power company. And then ultimately to your electrical outlet, to your electrical light socket, those kind of things where you've always got to have a hot wire and a neutral wire. And if you've got, let me back up to the other picture, if you've got a double wide breaker, well, then you're getting electricity from both of those black wires to give you 240 volts for central air conditioning unit outside. If you got an electric dryer to hook up, or an electric cooktop or oven, you're going to have 240 volts for those kinds of things. An electric hot water heater, maybe. When you go and defeat the grounding that we've been talking about, you are defeating a major safety feature of 3-wire grounding. When you got a 3-prong plug, it is designed to have those 3 prongs. So when you go remove the grounding point, like you see in this left-hand picture, that's not good. And yes, you can use a converter, converter grounding connector, like this one item in the middle here of the page. But you notice that green tab sticking up, that's supposed to be connected to a known ground. And so you're not supposed to defeat with those. It's allowing you to ground in another way when you use them properly. But nobody does that. And then, of course, you shouldn't have faulty cords and connections to plugs on the end of cords either. You got to make sure you got everything in good shape. So there's a few electrical terms. You could talk about the current is electrical movement. We measure in amps. The circuit itself, you're completing the path. You got to have a complete loop where you go from the supply of power to the return of power. You got to complete the circuit. So then there we can talk about resistance, the restriction to electrical flow. It's like the insulation on the wires. Conductors, substances, mostly metals that we use that conduct the electricity very well with little resistance to the electricity. Insulators, things like plastic or glass or porcelain, even dry wood sometimes, that prevent electricity from getting to unwanted areas. So the plastic on the insulation on the wires gives you insulation. That's what we mostly are familiar with. Grounding, a conductive connection to the earth that acts as a protective measure. It's a backup measure. It's not supposed to be your continuous path. It's only for emergency use. Electricity is a type of energy. Well, we knew that. It can build up in one place like static electricity, or it can flow to another place in what we call current electricity. So most of the time we're dealing with current electricity. Voltage is measured in volts with a letter V for the abbreviation, is a kind of electrical force that makes electricity move through the conductor, like the wire, make it move and push it through the wire. The more voltage, the more current will tend to flow, but it's a force. Whereas current is measured in amperes, or usually we just say amps, and we abbreviate that with an A. It's what moves through the conductor. That's the actual electricity that moves and flows. It's a steady flow of electrons. Now, when we talk about watts of energy, that's power. So watts we abbreviate with W, and that measures how much energy you use each second. So if you've got 100 watts of electricity being consumed, maybe 10 100-watt light bulbs, that's 100 watts of energy being consumed second by second. And if you do that for a whole hour, well, first of all, 1,000 watts is the same as a kilowatt. And so 1 kilowatt is 1,000 watts, but if you burn that 1 kilowatt for an hour, that's 1 kilowatt hour of energy on your electrical bill. That's how they sell the electricity to us, by the kilowatt hour. The resistance is a measure of how well a substance insulates, and we measure that in ohms, and we typically use that horseshoe symbol, that omega, I guess you could call it, symbol. It resists the flow of electricity, and so again, we're talking about insulation typically. So the voltage in the garden hose analogy, you may have heard, if you had a super high pressure water system where you could put tremendous stream of water out through a garden hose, and then you compared that to the fire hose that this guy's holding. But if you had it running at just a trickle, conceivably you could have the same amount of water flowing out of the garden hose as you do in that fire hose. So I don't have good pictures I got the opposite. One's at high pressure and the other one's at lower pressure. But that's the point is, when we're talking about electricity, water kind of helps you to kind of see that in some ways. And then if you have a really rough inside of that pipe of the hose or the garden hose or whatever, you're going to that's going to be a friction of sorts. And so the friction can kind of be the resistance that slows down and consumes some of the electricity when we're talking about electricity. So it's not a perfect analogy here. Amps times volts equals watts. And so that's a formula that electricians use all the time. They don't refer to it quite that way. They use a little bit different terminology, but it's the same thing. And this formula works for alternating current, like we have in our houses, or with direct current, like you have in your cell phone or in your battery of your car. And so, yeah, you can take 10 amps times 120 volts and you've got 1,200 watts alternating current, or you could, in your car system, have 10 amps times 12 volts and you'd have 120 watts. So the math works. The only thing it doesn't help you with is when there's surges of electricity that are needed to fire up an electric motor on something like an air conditioning unit, a refrigerator, that sort of thing. The surge of electricity for the moment when they first start up could be much, much more energy. It could be 2 or 3 times that amount of energy just to get started. Okay, that's enough of that. The 4 factors that determine the resistance of material to the flow of electricity. Well, what it's made of, what kind of metal or what kind of conductor are we talking about? Water we tend to think of as being a conductor. Not all water conducts. If it's pure water with no minerals of any kind in it, it doesn't actually conduct electricity. It's just that the water that comes out of your tap, most of the water you're ever going to deal with has enough minerals to conduct electricity. Its diameter, the diameter of the wire, the smaller wires, smaller diameter is going to have more resistance. It's not going to be able to carry as much electricity. Its temperature, if the wire heats up, it starts reducing its ability to conduct electricity, so there's more resistance. So that's the thing, as the wire heats up, there's more resistance, which causes the wire to heat up, so it gets worse and worse. So it's a spiral. And then its length. If you got a very long extension cord, a very, very long wire, there will be drop in energy. There'll be friction that builds up along the length of that line. So if you got a 300-foot extension cord, the voltage at the other end will be less than it was at the beginning. So yeah, electricity is generated at a power station, and there's distribution lines that transmit it to residential and commercial and industrial users. And at each point along the way, maintenance personnel must install, connect or disconnect, adjust, maintain the equipment used to generate and transmit and consume the electricity. And if a power line is cut down, maybe drops, gets broken because of a branch coming down, it can be touching the ground, touching a tree, and it can conduct through there and cause electrocution, even though you haven't touched the tree or touched the wire yet, because the ground can conduct it. So you got to be careful about your distance and keep your distance. So it dissipates the further and further away you get from the energy. And so you can kind of think of concentric circles from that wire emanating out, and how you've got to keep back and keep your distance. The high voltage lines are up at the top, lower voltage lines lower down, And then when you get to the area that I've got here, cable and phone lines, I've got them in the picture here, well, those are pretty safe wires because they're low voltage lines. They don't really conduct enough energy to do much to you. They just hurt your pocketbook if you cut them down or something, or if you accidentally hook on them with your heavy equipment. So the cranes, ladders, scaffolding are all in backhoe, scissor lifts, raised dump truck bed, aluminum paint roller, with a aluminum arm on it or whatever. Sometimes the craziest conductive things end up coming in contact with power lines, such as metal gutters. When people carry them around, suddenly the wind catches it and it touches some wires that you didn't intend to, and you get electrocuted. So you got to be very careful about handling or dealing with conductive anything that conducts electricity around these high voltage wires. You don't have to touch high voltage lines to get electrocuted. I kind of mentioned that with the ground being charged up. But just being near very high voltage transmission lines like you see in these pictures here, there is an electrical field and you can induce a current in the line. And so electrical fields can induce currents in you. And so the picture of the two characters here on this page, one is on dry ground at the right, and so that's why it's all green. It's not really conducting through him. It's just missing him. It's not really he's not affected by it. Whereas the other character is supposed to be underwater. Maybe I should try to draw a water line better than they had that stole this picture. But that's a case where you're well grounded, and then that electrical field could be enough to induce a current in you. So conditions can change. You can get sweaty where you conduct better because of the heat. So when we're looking at these transmission lines, they have greatly different amounts of voltage and unlimited amperage, generally speaking, at least as far as how we need to care about it. And there's these electrical fields that are in this picture here that the electrons don't like each other, and so they repel each other from the different wires, and they end up putting a strange pattern out that can be unpredictable to the average person. And so you can actually have an electrical field right there at the ground underneath these wires. So if you put a coil inside these electrical fields, within them, you can induce a current in that coil and actually steal power from the power company. Now, I wouldn't try it. Their lawyers are better than ours and stronger than any lawyers you and I can hire. They'll have a whole team of them, and they'll get you. So don't try that. But the point is that, yes, you can do it on purpose and sometimes we do, on purpose for a good, legitimate reason, induce current like that. Every transformer is inducing a current in order to convert the energy from a high voltage to low voltage or low voltage to high voltage. So we do this induction all the time in our electrical equipment. But when you've got a crane that's in the zone, you could induce a small current into the body of the crane, and a small amount of current as a percentage of the high voltage lines could still be a deadly voltage. And so if you're operating the crane, you're probably safe, like a bird on the power line. But when the operator steps down and touches both the crane and the ground, that's where they can run into trouble. Or some helper comes up to put some shackles and slings in a toolbox in the side of the crane and gets electrocuted. Or, like you see here on the right-hand side, you can have scaffolding that's in the electrical field of some power lines and induce a current in that metal frame. And so electrical current, it's no joke. These not just the wires that you touch, it's the wires that you are nearby, especially with higher voltage lines. So I was telling you about transformers. Well, in a transformer up on the power pole or the one that's on the ground that I showed earlier, there's a big coil in that transformer that creates a huge electrical field, and then they put a smaller coil and they size it just right so that they can get 120 volts coming out of those wires that you see on the side of that can here on the left side of the can. The outside wires are the hot wires and the center one is the neutral wire. So that's how they step the voltage down. So there's no actual electrical connection, direct wire connection between the energy side of our system and your side of that where your electricity is coming into your house. It's an induced current. That's how they step it down. So there are different safe distances to stay to keep protected. And I kind of put together some of this stuff from a couple of tables within the OSHA standards, table K1 and K2, and it kind of helps as a simplified version here. But the higher the voltage, the further away you need to stay. So that's generally true of all high voltage lines. When you get to when we start talking about general things for our purposes of our test and safety best practices, though, I've got a few numbers here. They're the ones that you need to memorize for a test. Two numbers, 25 feet and 20 feet. So we say we have best practices that say the approach distance when the voltage has not been determined should be 25 feet or more away. So if you don't know what the voltage is of that transmission tower, you need to stay 25 feet away. If you've determined by a qualified person, not just by guessing, that the voltage is 50,000 volts or less, then you should stay 20 feet away. So those are the answers to two different questions here. Watch that. If it's been undetermined, you stay 25 feet away. If it has been determined, you stay 20 feet away. I mean, if it's 50,000 or less. Well, 50,000 is still a lot of voltage. Going back to this table here, that kind of takes us into a range, and you see these numbers are lower. So these are looking at very minimal numbers, and there's not necessarily, maybe I shouldn't have this table on the page here, but it just gives you the idea of there's different kinds of notions here. But on your test, those are the two numbers. There's another old-fashioned way that you'll see, and I've tried to eliminate it from my course, but I still have a phobia that I may have missed one. And that is that we would often say stay 10 feet back from residential lines, and that's probably true. It's probably a good thing, but you'll find in safety training they don't mention it that way anymore. It's considered outdated, even though it's probably true in many cases. Again, the extreme cases, when you're standing in a swimming pool, you're much more grounded than you would be in other cases, and that can be a much more dangerous condition to come in contact with electricity. So it depends on a number of things. You see up at the top on the right-hand side, it says the true minimum clearance depends on the site conditions, such as exposure, grounding, and insulation. Okay, in most cases, water conducts electricity very well. I was talking about that. Well, our bodies are composed mostly of water, so our bodies conduct electricity well. You know, our body uses electricity to function. Our brain function, our nerves and muscles function that way. But, of course, too much electricity is not a good thing. This poor guy being electrocuted, well, I think it's staged, but it's pretty good staging. But look at the character on the right-hand side. This is the most dangerous condition. When you're touching a wire and you're well grounded in your feet or on your other hand, then the electricity is going to run across through your abdomen. And so that path makes this a much more dangerous condition, as opposed to maybe touching one finger and through another finger on the same hand. It's not going through vital organs. It's less life-threatening. You could still lose a hand if it's high enough voltage, but the path is a safer path. At least you're talking about sacrificing a hand instead of your life. So I've got that picture on this page too, and up at above that it says the severity of the shock depends on these three things. The path of the current through the body, well, that's what the picture down below is saying with the red dashed lines. The amount of current flowing through the body. So if it's a low voltage current that isn't just high enough to freeze your muscles and your heart muscles and everything, it can still be deadly. But then only if you've got duration. So the last one is talking about duration. So if you've got a long duration, 3 minutes or something like that, you could die from even a low voltage charge if it's 100 milliamps, a tenth of an amp, you know. Well, but if it's a very high voltage, duration will not matter. Electrical from one of those high voltage towers we were looking at, the amount of current is so high that the duration will not matter. Anybody here, well, ever gets suckered into touching their tongue to those terminals of a 9-volt battery? It will rock your world. It depends how you measure the battery, but batteries tend to send out electricity in a funny kind of way, so it's not quite so easy to do the math of what you're going to experience. But it is a significant shock to the tongue. I mean, that's not life-threatening. generally. Might change your taste buds for the day or something. But this picture that I have on the right-hand side is showing you the idea that drier skin is not going to conduct as well. And so you might, let's say, have 110 volts and high resistance, and you might only experience through your body 1 milliamp, something you couldn't even feel. Whereas wet skin, now the resistance is lower, and that same energy turns into 110 amps, which could be enough to freeze your muscles of your heart if it's going across from one hand to another or hand to foot, and literally stop it from beating and your lungs from working during that electrocution. And literally you asphyxiate, you suffocate, because there's no oxygen moving, because the blood isn't moving, and therefore you can die. Not you personally. Okay, so notice where I have the red asterisks in here. I don't know if I've missed any. I don't think so yet. But a severe shock, it says here over on the left-hand side, a severe shock can cause internal hemorrhages, tissue destruction, and fatal falls. It could electrocute you enough to make you fall, and maybe that's going to be what kills you. So there's going to be a combination of things then. Anyways, I put the happy face on this funny little character with the belly button and all that on the right side of the page one night. Okay. Now, when a bird is sitting on a power line, an individual line, there's no electrical potential difference anywhere. The bird is safe. But if that bird touches a line and maybe that power pole that conducts a little electricity, it might lose some feathers. You get a big enough bird or somebody or something. I've seen a bear on a power line, and when they touched the second wire at the same time, the bear did not do well. He dropped anyways. I don't think he died, but bears are pretty tough. But anyway, so the let-go voltage of people generally is around 6 to 9 milliamps. So you see this on this table, 1, 2, 3 or 4 lines down. You see the let-go current for women, let-go current for men. Well, what do they mean by that? Well, it's just that, well, women tend to be better hydrated than men. But so really and truly, you could say the let-go voltage, where you're going to notice it and want to let go, is somewhere in that range, depending on how hydrated you are. And then when we talk about the prolonged contact, when you step down to where you see 50 to 100 milliamps, well, first of all, let me back up and mention that, a milliamp is 1,000th of an amp. And your typical electrical outlet in your house will have at least 15 amp service to it. So we can take 15 amps, you got 15 amps of electricity there. And we're not talking about even 1 amp, we're talking about 1,000th of 1 amp of electricity. So 6 milliamps is not a lot of electricity. That 9-volt battery has that kind of power, It has more than that. It has 36 milliamps in ideal conditions. 50 to 100, where it says next to it, it says prolonged contact may cause collapse and unconsciousness. Death may occur after 3 minutes of contact due to paralysis of the respiratory muscles. So this is not enough to cook meat and flesh in your body. It's not going to be an instant destruction, but it is, if you're locked to it, what happens is your muscles tend to contract when you're being electrocuted, and you'll grab tighter to the wire, so you can't let go. And remember a friend of mine coming back from a weekend of working on his electrical on his kitchen, and he was putting under cabinet lighting in, and he was the only one home, so he didn't shut off the electricity. Instead, he just shut off the switch, and that meant that he was able to wire things up in this particular case without being electrocuted, except that his wife came home with the groceries while he was in the middle of a vulnerable position, hooking wires up, and he said, "It's dark in here," and she flipped on the switch and then continued to talk while he was being fried. And he said it felt like it went on for minutes, but it was really only seconds before he could let go. But he said it was all he could do to let go of those wires. Anyways, this 50 to 100 milliamps averages out to about 75 milliamps, which we tend to consider to be the dangerous average. So you could see that number, 75 milliamps, show up on an exam. I've got it marked somewhere else here, but 75 milliamps could cause death. But ultimately, dry skin on those prongs of the battery, you don't feel it really. But if you get wet skin, you touch your wet fingers to that 9-volt battery, you'll feel it there too. Okay, so the effects of electrical shock and arc and blast, well, Electrical shock may cause the heart stoppage or a fibrillation, an irregular heartbeat. So in order to shock the heart back into its proper rhythm, we defibrillate. So fibrillation is the irregular heartbeat. The defibrillation is where we shock the heart. And so these automatic electronic defibrillators, or AED devices, are a kind of a modern convenience now. You'll find in many, many buildings. Before COVID, we used to have one in each building. Now we have at least two in every building on campus. And so, again, as time has gone on, you'll find these things are more common. And they give you the instructions you need. And you can get first aid, CPR, AED training where you'll learn how to use these devices. This woman here is holding her hands back purposely when they're getting ready to actually do the shock. You don't want to join the party and get shocked. Your heart's already working properly when you're helping like that. Shock can occur in one of three ways. A person comes in contact with both wires of an electrical circuit, or one wire of the electrical circuit and the ground, or a grounded item, or a metallic part that is in contact with an energized wire or the ground, So a combination of those things, but ultimately the amount of resistance the skin provides can vary widely from individual to individual, but also different parts of the body. The hands, you could have calluses on, which will give you a smidgen of additional resistance. It's enough to make a difference when you're brushing by something, but if you're grabbing a hold of something, it's probably not going to help much. If you got moisture and sweat, open cuts or abrasions, that can reduce your skin resistance also. The shock occurs, it can be blood flowing through the heart, and that can be disrupted by electrical shock, like I mentioned. The severity of the shock received when a person comes part of the electrical circuit can be a real problem too. And of course, if you're being electrocuted by a huge amount of voltage, there can be cooking up of bone marrow and bones. It can be a lot of destruction. There can be entry and exit wound where you don't really understand just how much damage has just happened. And you think it's not that big a deal, but then you still end up getting body parts amputated. So it can be a very serious thing being electrocuted. So we have three different kinds of burns you need to memorize as testable points. Electrical burns are the most severe, generally speaking. Number one, so it says they result from electrical current flowing through the tissues or bone, like I was talking about, internal damage, heating up and cooking of the flesh and the bone marrow and everything else, ugly stuff. So tissue damage is caused by the heat. It's because your body is trying to heat up like a toaster wire. It's not good. It's not pretty. Since the most severe burning is likely to be internal, what may appear to be small surface wound could in fact be an indication of a severe internal burns. Okay, so that's electrical burns. Arc burns is where you're caught in the middle of an arc, so it's conducting through you. So there's an arc in midair. This arc is coming through you. And so that arc can be, in industrial equipment, it could be up to 35,000 degrees Fahrenheit, which is about 4 times the temperature of the surface of the sun. So very hot. And so it can be very severe, but it's just not as common for that to happen. It's much more common for electrical burns to happen. Then the third one is where a little more common than arc burns, and that's where equipment blows up, explodes, overheats from electrical energy. We call that thermal contact burns. Well, not the blowing up of the equipment, but if it burns you because of the shrapnel of objects flying at you that are hot. So you've got hot metal parts that are exploding like a bomb. And it's not just a hot object, it can be molten vapor metal fumes that are injected into your flesh, into your face, causing very serious disfiguring burns. So I know I'm getting kind of rough here, but you need to understand these things. So thermal contact burns, you're being burned by hot objects being thrown in the blast or metal vapor thrown. Backing up, the arc burns, we're dealing with being caught in the arc. And then electrical burns, you're actually part of the wire. You're part of the connection. You're in the circuit and you're toaster wire. You're the toaster wire. You're heating up like the toaster wire and it doesn't go well. So electrical burns, arc burns, and thermal contact burns. Just want to make sure you understand these three different things because they will show up on a test near you. Hint, hint. So this picture of this guy is showing the different places that we typically have contact during the electrocution. Your knees, your toes, maybe being grounded, and maybe your hands or your Often it's your hands that are touching the actual conductor, and so you can end up with an exit wound and an entry wound. And they're kind of showing you some samples. I think this picture at the top with the hand is actually showing a hand that may have to be amputated. It may be enough internal damage in there, but I'm not a medical professional. But this was an OSHA file photo. I think somebody lost their hand out of this one. Arc flash and arc blast. Well, electrical faults occur when there's equipment failures. Basically, two common types of electrical faults are the bolt faults and the arc faults. The bolted faults occur when a shorts out two conductors. So you can have two different conductors at different electrical potentials, the hot wire and another hot wire, or a hot wire and a neutral wire, or the hot wire and the ground wire. And you have a short, and it typically turns into an arc flash a lot of times. So it can be a serious thing. An arc fault occurs when electrical current jumps or arcs the air gap between two energized sources. So then you're usually talking about a high amount of energy for that to happen. And sometimes it's happening because something else is not conducting as well as it should, so it's looking for another way to conduct. Electricity will find its easiest path, whatever that might be. When you think about a lightning strike, the lightning tries to find the place that makes sense. There's no brain to it, but it's going to conduct wherever it can. So whenever a small arc is not interrupted and grows to a big arc, it becomes what we call an arc flash, kind of like a lightning strike. And that's where you can get caught in that arc, like we were looking back here at the arc burns, where you're caught in an electrical arc. Okay, so let's see, where am I here? The duration of the arc and amount, of course, that can affect the intensity. And just like we were talking about before, the arc flash can generate a very bright light, like welding, and in fact, it can be dangerous to look at in the same way as far as welding, just like welding. But it can certainly have temperatures up to 35,000 degrees. So you need to wear the right personal protective equipment. Emergency response. If someone near you is receiving an electrical shock, you should immediately shut off the power source if you can. If you can't do that, you try to find some non-conductive material like a blanket, a rope, a coat, piece of dry wood that you can separate the person with. Sometimes you can take the blanket or rope and throw it over top of them and pull them off of the electrical circuit. Pull them away. But you have to be very careful what you use, that you're not using something that will join you to the party. Let me kind of go to this picture of this poor guy being electrocuted. You go touch this guy on the left, you're going to be electrocuted. So don't touch the guy who's being electrocuted. You find a way to get them off, or cut the power would be best. Power cord insulation is subject to damage when cords are exposed to foot and vehicle traffic, sharp edges, there's a strain from being yanked on or pulled. Over time, the protective insulation on that extension cord can wear away or be cut, resulting in a shock hazard. So first of all, you're never supposed to tape up or repair a damaged power cord. You're supposed to replace it. The insulation that you get from using electrical tape is just not a substitute for the original insulation. So that's a legal issue. Yes, I've done it at times, and many other people have done it, and it's worked. So, but here's the thing, there's a liability issue now when you do that. And then the second thing is, that is not a permanent fix. Just like duct tape isn't a permanent fix, neither is electrical tape. I remember reading something a little while back where a guy put electrical tape on his brand new extension cords just so that nobody would steal them, because they figure they're all beat up. So that's a good reason for using electrical tape. So be very careful when using a power cord in a wet or damp area. Keep the cord out of the water. Electricity has been known to travel along the outside of a wet cord. The water itself on the outside of the extension cord can be a conductor, and so it could literally come back at you, and you're grabbing this wire that's actually live on the outside of the wire because of that. Especially when the water is, when you got the kind of Louisiana rainstorms we get, this can be a real issue. So of course, grounded plugs, and ideally 3-wire grounding, and GFCIs, ground fault circuit interrupters, are a very important way that we protect ourselves from these kinds of hazards and other hazards. 3-wire grounding, that'll trip the breaker, but long before that, a ground fault circuit interrupter will protect you. Avoid wet locations. Oh my goodness, look at that meter. Okay, let's skip along here a little bit. There's a frayed extension cord at the top. There's some bare wires here. And it's working for somebody, but no, that's a dangerous condition to have bare wires like that hooked up. The most common high voltage hazards are contacting overhead power lines with ladders, scaffolding, or heavy equipment, or contacting underground power lines with digging equipment. So 28% of these contacts, especially the overhead contacts, are fatal, and that can turn into a testable point. So remember that number. Anytime there's a number in this course, you really got to pay attention to that. You either know the number or you don't. You always contact a local power company or independent agency like Louisiana One Call before you dig. It's a free service. It's not free if you don't call them. In other words, if you don't call them and you dig up something, then you have nobody else to blame but yourself, and you'll be paying for that damage to the services underground. Remember, I gave it to you on another page, but here, in general, you don't maintain an approach distance of 25 feet or greater until the line voltage has been verified. So if you don't know what the voltage is, stay back 25 feet. Remember that number. Contact a utility company to shut down or insulate the lines. They can actually put a covering over the lines if needed, if you have to work near them. And a spotter might be needed to watch for that to prevent accidental contact with the power lines for the heavy equipment operator, because sometimes they can't see and judge distance well enough. Insulation and grounding are two recognized means of preventing electrical injury from equipment. So the conductor insulation could be provided by non-conductive materials such as plastic around the conductor insulation or covers. Grounding may be achieved through the use of a direct connection to a known ground, such as a metal cold water pipe or that 5/8 diameter copper rod that we drive into the ground. And every house has one, so you can use that. You can literally go and connect up to it. If you got a generator, you should generally be connecting that generator up to the grounding rod that your electrical service is hooked to. That's what you should connect to every time you use a generator. Using tools powered by a low voltage isolation transformer can be another way to avoid the risk. Now this picture you see on this right hand side of the page is a cross section of a double insulated power tool, a drill, but it's showing you in red the areas that are isolating you. So the switch that you pull, the trigger, that's isolated, and then the whole tool is isolated. So you are twice removed from the electrical equipment. So that's why we call it double insulated. So they aren't grounded equipment. Instead, they go the opposite way and they twice remove you from the electricity. So double insulation may be used as an additional protection on live parts of a tool, but it does not protect against defective cords and plugs or against heavy moisture conditions. So the best thing overall is to use on a construction site or around your house ground fault circuit interrupters, GFCIs. They overcome the grounding and insulation problems because they're so sensitive they will trip instead of electrocute you. Okay, let me skip along a little bit more. GFCIs, I'm coming to an area where I want to talk about them here. So yes, here we go. Minimizing the risk associated with working around electricity. Well, a GFCI, a ground fault circuit interrupter, it's a fast-acting circuit breaker, basically, and they can be portable like you see here, or they can be built into the wall in your kitchen, in your bathrooms. They're supposed to be, the electrical code requires them in wet locations, in bathrooms and kitchens, carports, garages, outdoor outlets, all have to be protected. Now, if you got an old enough house, you don't have that kind of protection, but you can add it. You can install it back in there on your own. So whenever the two values differ by more than 5 milliamps from the hot wire to the ground, the GFCI will trip within 1/40th of a second. That's pretty quick. A second is pretty quick. 1/40th of a second is hard to imagine it's so quick. So before you can feel it. And 5 milliamps, you're barely going to feel it if you can feel it at all. If you're very sensitive, you might feel the 5 milliamps, if it was continuous, you're not going to feel it when it's only there for a 40th of a second. So it's very safe. They're an important safety device. There's also something called an AFCI, and these are typically circuit breakers. You can have GFCIs that are circuit breakers also, but the AFCIs are distinguishable by that white neutral wire. You normally don't see white wires at all associated with circuit breakers, but with the AFCI circuit breakers you will, because they have to have a neutral wire for them to be hooked up properly to work. So the AFCIs, if you go down to the third bullet here, they protect against line-to-line hazards. Remember, the ground fault circuit interrupter only protects against ground fault from line to ground, but the AFCI can detect line-to-line hazards too, and so they're very sensitive. They're only used in, originally they were only used in bedrooms, and eventually they started adding them to everywhere, because basically the AFCIs, the arc fault circuit interrupters, they prevent fires. They prevent your cords heating up like toaster wires because they're sensitive enough to detect that behavior and trip. So the double insulated tool we were talking about, here's another example, and you see there's a symbol up at the top right hand corner for double insulated tools, and they typically are 2-prong plugs, and they're typically polarity plugs, where the hot wire is hooked up to that brass colored prong at the top there, and then the silvery prong is, and it don't have to be this color, but the silvery prong in this picture is a wider blade, and so it's meant to make sure you can only plug it in the outlet one way, so that the hot wire is going to always be the brass one, and the neutral one will be always that wider blade. But anyway, so that's another level of safety, so that they protect you. We also have something we call double insulated in hand tools, and all that means is they have twice as much insulation on them, and they'll put as much insulation everywhere as they can, and it's generally for electrical protection. So electricians tend to use double insulated tools, including screwdrivers that'll have insulation going all the way down the handle so that you're not going to accidentally touch the shaft on something and short out something. You see on this electrical outlet here on the bottom, a real picture of one, how the hot wire is a smaller slot, the shorter of the slots, and the longer of the two slots is the neutral wire. And so you see that reflected in the colors of the screws. The brass colored screws is where the hot wires get hooked up. The silvery screws you see on the bottom, I've got it turned sideways here, it's normally not this way, but the silvery screws will be the neutral wires. And then there's a green screw over on the right hand side here at the bottom that is the ground wire screw. And this is how these things are hooked up. Let's see here. So here's some more examples of GFCIs of different kinds. Now, the electrical outlets on the bottom left. And here on this page, I've got a couple of things in asterisk forms. I've actually talked about a couple of these things. So let's go look at that third bullet. It says, if a ground fault is detected, this is a testable point, the GFCI shuts off the electricity in 1/40th of a second. I mentioned that already. If it detects a small current leakage of as little as 5 milliamps. So those are a couple of numbers to know about that. I don't think I'll make a really tricky question out of that, but you still want to make sure you know these so you recognize it well. The next one I haven't quite mentioned, but this is how they define. They're kind of their description or definition almost of a GFCI. GFCIs, where they're used, I guess you'd say, is on all 120 volt single phase 15 and 20 amp receptacles, or you could have an assured equipment grounding program. Okay, well, that's something I haven't really talked about yet. But before I leave this page, over there on the bottom right-hand corner, you see the orange tester. That's not a GFCI, that's a GFCI tester. Well, it's actually an electrical outlet tester. It's a fancy one with a digital screen. That's nice, but it has a test button on it. Well, all the GFCIs have test buttons on them, but over time they can fail and not give you an accurate test. So it's good to do an actual test with a device that's independent of the outlet. And the other thing I could like to point out is that yellow GFCI, portable GFCI down at the bottom, has a splitter involved, and that's generally not a good practice because you're really supposed to plug these GFCIs in at the source. And then you put your various cords into there, because otherwise the cord's not protected. And if somebody jams their shovel through an extension cord, they could still get electrocuted because the GFCI won't be there to protect them. So you always should be plugging in the GFCI to the source, and then plug your cords into that. Now, you're allowed to use a tool directly with no extension cord by plugging it directly into a power source, because the power source of a building is assumed to be already protected. But it's not always. I've kept a little device kind of like this orange tester, or a simpler version, with me, and I found plenty of buildings that weren't wired properly and certainly weren't protected. The Assured Equipment Grounding Conductor program that I was talking about, the program must cover all extension cords, all cord sets. They all have to be tested. Receptacles that are not part of a building or structure, they have to be tested. All the equipment, so your skill saws, circular saws, drills that are AC powered, your table saw, all of your tools and equipment have to be tested periodically. So what they do is they use a system like you see down here at the bottom, where they could have a quarterly system where every quarter you test every piece of equipment. And so they'll use color codes, because they typically will take some white electrical tape and tape it around the shaft of the drill cord so that you see that white color and you know it's been tested that quarter. And then if not, then you don't use it. Well, often they'll allow 2 colors to be used so that they go through a transition period. Now, a better program, and more common, I think, nowadays, is to have a monthly program so that you have a color of the month and you can use last month's color too. But the idea is it's kind of like herding cats, trying to go around and test all this equipment during the day when people are using it. So you grab the equipment as you can, and by the time at some point, you're getting to a point where you've tested all the equipment. This equipment is tested by a qualified person. That generally means an electrician. An Assured Equipment Grounding program deals with testing all this equipment with meters like you see here. And the OSHA actually requires that a written description of the employer's Assured Equipment Grounding program be kept on their site, generally as part of their site safety plan. The 2 tests that are required by the Assured Equipment Grounding program one would be a continuity, and the other one is grounding protection. The equipment grounding, making sure that it's a continuous ground. So it has to be performed on all this equipment, as we said, that we were saying. And these are typically the tools you might use. So the continuity tester you can use, but you can use most multimeters as continuity testers. And so typically a meter is used for both, I think, in the real world. But this stupid little continuity tester could test for continuity to make sure there's no shorts, there's no loose wires and that sort of thing. The second test I've got listed over here, plugs and receptacles are checked to ensure the equipment grounding conductor is connected to its proper terminal. So that little tester that I was showing you for the testing of the GFCI tests for continuity also, and tests to make sure that the outlets are wired correctly. So it's a handy little tool to have. It is not expensive. Workers must be aware of and select the correct meters with the appropriate category rating for any overvoltage condition likely to be encountered. Okay, that's a mouthful. So we have this category system you see in this table on this page here, Cat 1, Cat 2, Cat 3, Cat 4, all in Roman numerals. So it's I, and I, and IV. Okay. Lousy joke, I know. But anyways, so what you need to know is that about this system is that Cat 1 meter gives you the least amount of protection, and Cat 4 gives you the greatest degree of electrical protection as you use it. And everything else is somewhere in between on that graduated scale. So remember, Cat 4, as you see down at the bottom of this page, provides the greatest degree of protection. So if I go over to, well, let me back up to the other meters. I think that the continuity tester would probably be considered a Cat 1 meter. It doesn't give you hardly any protection. You could send all the electricity through and have no fuse possibly in that thing. This other multimeter that you see says Cat 3 on it down near the bottom right corner. No, I'm sorry, Cat 2. because it's a pretty cheap meter and probably has a pretty cheap fuse in it and that sort of thing. This next meter over on this next page is a very high quality meter, and it's a Cat 3 meter. So multimeters generally are not going to go any higher than Cat 3. If you get an electrical field tester that has no metal on it and you're testing electrical fields, those are rated as Cat 4 meters. So remember that category system that's over on this page, mostly to remember that the greatest degree of protection comes from Cat 4 and the least is Cat 1. If you remember that much, you'll do fine on that test question. Okay, nice meter. Okay. When we're talking about minimizing the risk associated with electricity, the distance, keeping your distance is your best protection against high voltage electrical hazards. There's plenty of other things on this page, and I need to kind of move on here a little bit. The two types of boundaries we talk about are the arc flash boundary and the shock protection boundary. And you want to be far enough away from an arc flash that you're not going to have shrapnel flying towards you or molten vaporous metal. And then the shock protection boundary is a lesser distance, generally speaking, but it depends. When we're talking about very high voltage, the electrical field is a very real and serious danger. So this person you see in this picture is in a special electrically safe suit. This is not a hazmat suit. This is an electrically isolating suit that can take the arc blast and some of the shrapnel that can fly against them, plus it's electrically insulating. And so when they don't know what the voltage is, or if they're not sure if the equipment is on and they have to go and check that out, they can wear the suit until they're sure that the electricity is actually shut off. And then they can take the suit off, just like the rest of the people who are going to work on the equipment. Okay, and so yes, there's special equipment. Here's that suit again, and there's other things, the electrically insulating gloves that they wear, and then there's a leather glove protectors that they put over top of them. They're thin leather that they put over top of that. Special shields of various kinds. And then just for general work with electricians, you wear electrically insulated boots, a higher degree of insulation for your hard hat, and again, the same kind of gloves we were talking about. You wear the rubbery gloves. You got to test them to make sure there's not any leaks in them, because any pinhole prick of a leak in that rubber glove, the electricity can find a way, just like lightning can find a way to ground. It can still arc through. And then we protect those rubbery gloves from getting those leaks by wearing a protective thin leather glove over top of them. And then, when you're going to work on equipment, one of the main reasons we lock and tag out equipment, we have a lockout tag out process, is for electricity. It's not the only reason. So in a lockout tag out process, we'll talk about that in detail later, but a lockout tag out process, it protects people from unexpected releases of energy during the servicing or when you're working on any kind of equipment. So just like you shouldn't be working under the hood of your car until you've disconnected the battery, you certainly shouldn't be doing that when your friend is sitting in the driver's seat with the keys in the ignition, right? You don't want that thing to fire up when you're under the hood. It's the same concept with any other kind of equipment you're working on. And the best way to make sure that it never gets turned back on when you're not looking is to lock out the device so there's no way anybody can do that unless they have the key. So the basic process here is you lock out the equipment after you've de-energized everything and you're sure it's off, and you put a tag on it so people understand it's an official process and not some prank on April Fool's Day or something, so nobody's going to cut that lock, is the idea. This particular hasp that's on there allows you to put 6 locks on there, or you could put another hasp on there and add more locks. But at some point, or maybe in many cases, maybe you can only put 1 lock on a device, and maybe you can't do something like this. Well, then you can put that key inside of a lockbox, and then you lock up that key in the lockbox, and everybody puts their padlocks on the lockbox as a way to keep anybody else from accidentally or when they're in some miscommunication unlocking the device. And so this picture on the right-hand side is showing you a lockout tagout kit. But there's a lot of different kinds of covers, depending whether you have to lock a valve up so nobody can turn that valve back on. So that shroud that you see at the very left-hand side, the furthest thing in that picture, is meant to go around a handle of a valve. And so a lockout tagout process, the person who puts the lock on the device is the only one that should be removing it. And they keep the key, and they shouldn't be using combination locks. And generally in the plants, they will use a very specific lock and have a rule that nobody else is supposed to have a lock that looks like this, so that everybody recognizes through their training, their safety training, that that lock is something that you're not supposed to be messing with because it's a lockout tagout lock. And generally you'll also have their name or a number that identifies the person, identifies the lock, so you can tell who the lock belongs to. The severity of the shock. Okay, I've got some kind of a summary here at the end of this presentation. And of course, a lot of this stuff is also in the study guides. But here I'm just going to go through it since I'm here. So the severity of the shock depends on the path of the current through the body. Remember that. We talked about that. The amount of current flowing through the body in amps. The duration of the shocking current through the body. Of course, that matters more if it's low current. If it's a very high current, the duration will not matter. Next point, when the tools or equipment touch overhead high voltage lines, 28% of the injuries are fatal. Remember, there's a number, so you better remember it. Next point, electric shock may result in immediate heart stoppage as a result. The next point, fibrillation can be caused by an electric shock of as little as 75 milliamps. So fibrillation, that's the irregular heartbeat. And then, of course, defibrillation is where we shock the heart back into a normal rhythm, hopefully. The next point, a severe shock may cause hemorrhages, tissue destruction, or even a fatal fall. Because if it makes you fall, then that may be how the fatality happens, and it's still related to the electrical issue. Low voltage does not mean low hazard. A severe shock can cause internal hemorrhaging, tissue destruction, and a fatal fall. Well, they're two separate things. Generally, we're talking about a higher voltage when that happens, but a low voltage could just freeze the muscles, stop the heart from beating, stop your lungs from working, and you literally asphyxiate while you're being electrocuted for minutes. So generally a 3-minute, 7-minute, certainly 3 minutes is kind of getting to the line. If you just think about how long can you last underwater, and you get a kind of an idea how that might go. Okay, next page. There are 3 different kinds of burns. You remember this was important before, so here they are: electrical burns, arc burns, thermal contact burns. So remember, the electrical burns can be the most severe types of injuries. There's internal damage through this tissue and bone destruction, the electricity flowing where your body is heating up like a toaster wire. The arc burns, you're caught in the arc of the electricity, a big bolt running across the room, and you're caught in it. So that tends to happen when you're about just a few feet away from some heavy equipment that arcs out. And remember, that temperature is 35,000 degrees in that arc in the extreme cases, 4 times the temperature of the surface of the sun. And then finally, the thermal contact burns are where you're in contact with objects thrown during an arc blast. When there's an explosion of the electrical equipment, hot objects or molten metal vapor thrown and injected into your skin and then burning you. So it's thermal because it's hot. The parts flying at you may be an injury, but when it's hot, it's adding insult to injury. And then I added in this thing here, lockout tagout devices are meant to ensure that equipment cannot be started while being serviced or repaired. That's the whole goal of using lockout tagout equipment. And one more page. Remember that grounding thing I was talking about. The NEC 250.52 through 53, that's the NFPA 70, requires 8-foot grounding rod, 5/8 in diameter, made of copper, driven into the ground, or a 3/4-inch pipe driven completely into the ground. Either way, 8 feet of it, or you take the whole 8 feet of the rod and you bury it 30 inches underground. That's 2.5 feet. or you connect up to a 20-foot piece of rebar that's embedded in the concrete with direct contact with soil. So you can't have a vapor barrier then. So most house slabs and building slabs wouldn't qualify. Next line is the definition of grounding. Grounding may be achieved by directly connecting the ground circuit to a known ground, which is normally a 5/8 inch diameter copper alloy rod. Next point, we're getting close to the end here. Use ground fault circuit interrupters, or circuit interruption, GFCIs, to protect against ground faults. And the next point about GFCIs, ground fault circuit interrupters are needed for all 120 volt single phase 15 and 20 amp receptacles if they are not part of the building or structure. And the last point is really about that thing I just mentioned about the category ratings here. Electrical testing meters are rated by category. Cat 4 meters provide the greater degree of protection for a user compared to the Cat 1, Cat 2, or Cat 3. So Cat 1 is the worst, and it scales up from there. Okay, so there we are, finally at the end of electrical protection and prevention.